Welcome to Unit 5, Lesson 4, Tables, Equations, and Graphs of Functions. And my 11th attempt at recording this video. I hope this time it actually loads. I'm not trying to complain to you. I'm going to go pretty quickly on this one. What do you notice and you wonder? Doubling back, we can take a look at this graph and we can take a look at a couple things with it. And when I see a couple things, what do I notice? I notice that the lines aren't straight. I notice that the graph appears to be coming out from two different points to one single point about 200 looks like 200 meters from some starting line. I can notice a lot, but first thing I see with this is that I don't see straight lines. I have no idea what this is supposed to represent other than somebody's taking a distance from a starting line. So maybe it means moving from this point at the starting line, running or jogging or driving or something out to this point and returning back to the starting line. That's all I can know. The next section of this is talking about the graph of three functions. And these three functions, we are going to actually be checking them against some other information right here. So I apologize they're not on the same page, but here's what we're after. We're supposed to match up each of these three descriptions with one of these graphs up above. And so what I want to do with this is let's take a look and recognize a couple of things. First off, letter A says D is equal to 60t, where D is the distance in miles that you would travel in t hours if you drove at 60 miles per hour. Well, recognizing that this is a constant rate, that means that this is going to be a straight line. I would also recognize that I'm starting at 0, 0 because there is no y-intercept. It just means that we're driving 60 miles per hour somewhere. And so when I look at this, I'm looking at the graph of B. And when I look at that graph of B, I'm supposed to a little bit later label the axes. So I'm going to go ahead and label these right now. This is going to be distance in miles that you would travel in t hours. So I'm just going to say driving hours or driving time. Should just say time. And this is in hours. And then this is my distance in miles. Okay. Letter B, Q is equal to 50 minus 4/10 of D, where Q is the number of quarters, D is the number of dimes, and a pile of coins worth $12.50. Again, this has to be something linear, and as I look at this equation, I see a y-intercept of 50 and a descending or decreasing slope. That means that it can only be C. And so right here, when I say that we're looking at the number of quarters is equal to, and I see that dimes is the variable that's attached to the slope, that means that when we look at this, we're talking about the number of dimes is the x-coordinate or the independent variable, and then in this case is the number of quarters, because that's the outcome or the output that we're actually looking for. And it's all simply because of the way the equation is written, saying the number of quarters is a function of the number of dimes. That leaves us with this last one where we have an exponent. This is where we find the area of a square, or the area in square centimeters of a circle is with the radius r. This is graph A. We would say that this is the radius in centimeters. And then we would have area in centimeters squared. Okay, so I labeled each of the axes with the independent and dependent variables and the quantities that they represent. That's problem number 2. And then problem number 3, it says for each function, what is the output when the input is 1? That means I need to go back in there and I need to go back and I actually need to use some substitution back into those equations that were given. And so when I look at these, when the input is 1, what does this tell you about the situation? Label the corresponding point on the graph. When it's 1, let's just go like this. For A, we have area is equal to pi times the radius of 1 squared. That would mean that the area is equal to 1 times pi, or the area is approximately 3 and 1400 centimeters squared. For B, we're talking about the distance is equal to 60 times 1 hour, so the distance is equal to 60 miles. And for C, we're talking about the number of quarters is equal to 50 minus 4/10 of 1, which means the number of quarters is equal to 49 and 6/10, which that kind of, all right, we'll talk about that one in a second. And then we're supposed to graph those, label the corresponding point. What does this tell you about the situation? So what this tells me is that in this situation, when I have a circle with a diameter, with a radius of 1, that the area is about 3 1400ths. With 1 hour driving, we have 60 miles of distance, and with 1 dime, we have 49 6/10 quarters, which is just really bothering me. I'll come right back to that. But this one right here is when R equals 1, area equals, not equals, is about 3.14 cm squared. When the hours, the time, equals 1, the distance is 60 miles. And this one, when I have 1 dime, I have 49 6/10 quarters. Okay, 2 or more input-output pairs. What do they tell you about the situation? Label the corresponding points in the graph. Well, if I look at these other pairs, I'm just going to go ahead and put a couple of them on here. If I take 2 and I go ahead and substitute right here, all I'm going to do is be taking that radius of 2, I'm going to square it to 4, and then I'll add, and then I'll multiply the value of pi, which is going to give me about 12.75, okay, times to my area, and it's just going to increase a little bit along the line. I could say the same thing for 3, although just reading the graph isn't going to be very easy to work with, but I would say 3 squared, 9 times pi is somewhere around 27 and 45 hundredths or so. But it's something that we would have to be able to calculate exactly to be able to work, and that's why the equations are so useful. Driving time, 2 hours is going to be 120 miles. 3 hours is going to be 180 miles. The quarters, that's the thing that is really getting me. This one right here, we actually can't draw a graph of a line for the quarters and dimes because this can only be done in whole number values. So when we say we have 1 dime, how many quarters do we have? That's not going to work for a possible combination because it gives me a decimal value for the number of quarters. I would have to locate and find only whole number values that would actually work for this. And so those whole number values, when I find those, they would be things that would be something like, hold on, I wrote these down because I went through and worked with these, and now I can't find it. It would be something more like we would have to have multiples of 4 to be able to work for our quarters. And so when we think about that, we want to go along these values and we want to substitute in only input values that are going to give us whole numbers. One of those indicators would be like this. If I had 40 dimes, that would give me 10 quarters left. Okay. And, 10 dimes. That would give me, like if X was 10, if X was 10, that would give me 45 dimes, approximately 45 quarters, approximately. Because what I would be doing, 46 quarters, because I would be taking away that value right here. 10 times 40, or 4 tenths is 4, and 50 minus 4 is going to be 46. Sorry. So if I take 10 dimes, I have 46 quarters. If I take 40 dimes, how many quarters would that leave me with? Well, 4 tenths of 40 from 50 would give me that outcome, and I could come in here and I could approximate it, and I could see that it's going to be somewhere between 30 and 40. I could continue to do that, but the thing that really frustrates me on this one is that when I see that decimal number, I get frustrated because I think, well, that's not possible. Why didn't my solution work? Well, it's a true solution for this function, but not every solution is going to be true for the situation. So you have to be careful to pay attention to that, especially when we're talking about input and output pairs. And what do they tell you about each situation? What that tells me, and really the big thing, really anything goes for A and B because those are all constant and consistent. But letter C, whole number values only. All right, that's enough of that one. The last thing I want to do, I am skipping that other part because we don't want to do that are you ready for more type of thing. This is talking about Kieran running around a track. The graph is shown with the time T he took to run various distances. And we can see that over an amount of time, there's a lot of information we can look. That same information is going to be over here on this table, and we can get that information from here. So how long did it take Karen to run 6 meters? We just look for 6 meters on the table. Distance of 6 took him 2 seconds. How far had he gone after 6 seconds? So I want to look at my time, and I find 6 seconds, and we find out he went 18 meters. Estimate when he ran 19.5 meters. 19.5 meters is actually exactly halfway between 18 and 21. And so if we're talking about 19.5 right here being halfway, then halfway between 6 and 6 and 49 hundredths, or 6 and 9 tenths, is going to be 6 and 45 hundredths seconds. And if we talk about how far he ran in 4 seconds, I'm going to be looking for 4 seconds. 4 seconds is somewhere between 12 and 15. It's not right in the middle of 12 and 15 because the 4 seconds is going to be closer to this 4 and 6 tenths. I would estimate this is more like 13.5 meters. Is Karen's time a function of the distance that he ran? Yes, it is. The reason that it's a function of the distance in this case is because everything is running at a rate that's not going to repeat any input values. The time is directly dependent, or a direct output, the distance is direct output of the time that he spent running. And then that speed, we can't say that he had a constant speed because this line for his graph is not a straight line, but we can see for a fact that his distance, or the time, came as a result of however far he ran. So the time was dependent on starting and stopping with his distance. Okay. Let's look at Priya. And when we take a look at Priya's information, here's Priya's graph. She's running once around the track, and the graph shows her time and how far. So this is kind of an interesting graph. This is the same one as what we saw, but what we know is that Priya is running around a track, supposedly an oval one. Starting line is usually right here. And so she's running around that track. What was her furthest distance from her starting point? Well, her starting point obviously is here at 0, 0. It looks like she ran the furthest distance that there was is 200 meters, which makes sense considering a track all the way around it is 400 meters. Estimate how long it took her to run around the track. Well, if she came out here to 200 meters and then she came back to the starting line, it's only fair to assume that this was her ending point as well, and that it took about 75 seconds. And when she was 100 meters from her starting point, it is a problem because we have 2 different points. At this point right here, when is she 100 meters from her starting point? It looks like 13 seconds and probably like 50-ish seconds. I'll explain why that's a problem here in a second. Estimate how far she was from the starting line after 60 seconds. Well, once we get after 60 seconds, we can take this one right here, come to the line, and it looks like she was 75 meters from the start. Now, is Priya's time a function of her distance from her starting point? In this situation, no. And because what we're saying is time, the function of her distance related to the starting point, the problem is no, because the starting point and the ending point are the exact same spot. In a function, the input can have, you can't even see that, at most one unique output. What that means is that the inputs, think about the function machines that we've been doing. If this is the function machine, her input coming to her output, there's an input of 100. But the problem is that output, it has to follow a certain rule, and that rule can only have one outcome. There's only one possible way to make this rule true. And so when we talk about that rule, if this is true, let's say if we're talking about from 0 to 200 meters, with right here, that's one aspect of it. But the fact that along the way, that 100 meters from the start, that's the exact same distance from the starting line, but it has 2 different outputs. And so this little function machine that we're talking about, following that rule, That rule cannot be followed if you have two different outcomes, right? There's only one possible output when we're talking about an input in a function machine. So pay attention to that piece. That's the big learning from this lesson. Our summary is going to relate much like the previous question that we saw with, oh my goodness, I just forgot his name, with Kieran. And it just displays and reviews through these pieces. But the bottom line is this: all coordinate pairs are inputs and outputs. They're always plotted on the coordinate plane. What we recognize from this is the input is always first, which means that the inputs are represented on the horizontal axis, or your x coordinates. Outputs are always second, or your y coordinates. Don't forget, functions are always going to be one in or one output for each input. A simple test that you can use is what's called the vertical line test. And that vertical line test means this: if you take a vertical line across any graph and you see any 2 points that lie on that same vertical line, it is not a function. And here's a good example of that. We have 2 points along this vertical line all the way through until we get to the very end, which means this is not a function, but this one is. On a table, you're totally okay to see the same number repeated in the outputs, but not on the inputs. That's all I got. Good luck. Let me know how I can help on any questions.